Hello and welcome to lecture 22 of CS135. Alright, so a few things I'd like to mention before we get started. First off, don't forget assignment 9 is due tomorrow. And you'll note that assignment 9 is requiring that you do not use explicit recursion. You have to use our abstract list functions of map, filter, fold R, fold L, and build list as appropriate. And pay attention to each of the questions, as it's very common for us to say you must solve this problem with this particular abstract list function. And if you don't solve the problem with the correct abstract list function, then you can anticipate losing a large portion of your marks for that. The other thing I wanted to mention is your final assessment, and I know I've mentioned this a few times already, but your final assessment, again, it is completely optional, but I highly recommend that you do it because you have absolutely nothing to lose. This is how it's going to work. Now, the assessment should be available on April 8th, and I will post more to Piazza about this shortly. And it has two parts. The first part of the final assessment is a quiz on Learn, and you will have 3 attempts for the quiz. And it's asking, questions, theory questions, things that we've done so far. And then that's going to comprise about 25% of the final assessment mark. The remaining 75% of the final assessment mark comes from a coding problem that you will have 10 days to complete and submit. The reason why I recommend you do it is it can only be used to improve your mark. So if you look on the course website, we now have 2 marking schemes. And if you don't do the final assessment, then you won't really have any option as to which of the grading schemes that is applied to you, because your final assessment score would be 0. So you probably end up with option 1. However, if you do the final assessment and you do really badly, then you still get the maximum of the 2 grading schemes. And if you do the final assessment and you do really great, it gives you an opportunity to actually pull up your marks. So we're going to take the maximum of the 2 options, and that will be the grade that you get. So I think that's actually a pretty fair deal. So I highly recommend you do the final assessment. All right. Let's then move on to doing some review. So we're going to try. I apologize if there was errors. I'm actually so there's a bit of lag. Or the tower using different Now, looking at this graph here, there's a few different things that we should label. First off, we have nodes, which nodes are often referred to actually as axes. And then in our graph, we also have things called edges. And edges are what connect the nodes together. Now, what's interesting about the particular graph here is that this is have a direction. They have an origin and a destination. So I have an goes A, C. So I can actually go to C the opposite from there is so we can take the directed graph and we can create what's known as an adjacency list. And so I'm going to make a little space here, and I'm doing this in Racket because it'll be a little bit faster. What you can see here is for the graph that we had just a second ago, and there were 6 nodes, and we want to represent it as a list of pairs, key value pairs actually, where the key is the name of the node and the value is going to be the list of out neighbors that each of that particular node has. Now remember, for a directed graph, there's the concept of in neighbors and out neighbors. In neighbors are nodes that have edges to you, and out neighbors are nodes that you have edges to, so places where we can go from you to somewhere else. So in our graph from before, this is how we would actually represent that graph. So node A had 2 out neighbors, B and C. And then node B had 2 out neighbors, being D and E. Node C had no out neighbors, and you'll notice here that when we represent a node that has no out neighbors, we actually do need to put an empty list to indicate you have no neighbors, at least no out neighbors. Node D had a single out neighbor of F, forgetting a bracket, and then E had also a single out neighbor of F, and then F has, again, no out neighbors. So this here is actually our adjacency list representation for the graph I drew just a few short minutes ago. So now that you've seen that particular adjacency list, there are some other things that you need to remember. There are lots of properties that graphs can have. So graphs don't have to be directed. An undirected graph means if you have an edge between A and B, then you can travel from A to B and B to A. Whereas a directed graph, you would actually have to have separate edges for each of those. There are graphs which are cyclic, that is, they have cycles that go around in loops. And there are graphs which are acyclic, which means they don't have any path that would result in you returning to your origin. Then we also have connected graphs, and the graph that you saw just a minute ago was actually a connected graph because all of the nodes are actually connected into one piece. And if we had a node that wasn't connected or some other subgraph that wasn't connected to the main one, then that would be a disconnected graph. So there are lots and lots of different properties associated with graphs. So what I'd like to do then is let's look at the following clicker questions, which I know you don't have a clicker, but let's just talk about these. So I want to know which of the following things are graphs. So I have a binary search tree, a list, and a forest, and a set of unconnected nodes. And I'm going to tell you the answer is all of these could technically be implemented as a graph. So binary search trees are a tree, and first and foremost, trees are graphs. Trees are graphs that have a single origin, which in a graph there is no concept of a singular origin. We've just added that extra constraint to create trees. A tree has no cycles. There are graphs that have no cycles. So trees are actually a kind of graph. So a binary search tree being a type of tree means it is also a graph. Lists. Now this one's kind of a stretch for some people, but if you think about it, each element in a list is actually a node. And the edges are the connections between this and the next node in the list. So a list could technically be considered a graph in some ways. And in fact, you could implement a linked list or a bracket style list using a graph. I'm not sure why you would, but you could absolutely do that. Then we have a forest. Now, a forest is a bunch of trees, but those trees are not connected together. And since each tree is a graph, and since we do not require that graphs are connected, a forest is a graph. Now, a set of unconnected nodes, remember that graphs do not have to have edges. Graphs do not have to be connected. So if we just have a bunch of nodes and they're not connected, it's probably not a very useful graph, but it is still technically a valid graph. So the answer is all of the above. All right. So we have this graph here, and we've given it as the adjacency list representation. So I have 3 nodes, A, B, and C. And A's out neighbor is B, B's out neighbor is C, and C's out neighbor is A. And what I want to know is what is true of this particular graph. And we have 5 options here. We could say it is not a directed graph. We could say it contains a cycle. We could say it is a directed acyclic graph, or we could say it is disconnected, or none of the above are true. The answer is B. Only one of these is actually true. It is a directed graph because that's what we are representing here. We have in neighbors and out neighbors. Is it a directed acyclic graph though? No, because if you actually look, we have a path from A to B, B to C, and then C back to A. So we actually do have a cycle in this graph. We're going to come back and look at this graph a little bit later. Now, the last option is it disconnected? It's not disconnected because all of the nodes are actually connected together. All right, so that is that for those little questions. So what I want to do now is let's do a little sample problem. So if we go back in your notes, let's bring them up here. Here's our notes. We gave a data definition for a graph as a node is a symbol and a graph is one of empty, or consing of the pair, which consists of the node and its list of out neighbors, onto another graph. Essentially, a graph is actually stored as an association list, where the key is the name of the node and the value is the list of out neighbors. So this was our data definition for the graph, and then we provided you with a template, which was missing the list of node template, but it is a fairly standard template that we showed you last class. So now what I'd like to do is I'd like to write a function that doesn't just give you the list of out neighbors for a particular node. I want to know for a particular node that exists in the graph, I want to know not just its out neighbors, I also want to know all of its in neighbors. So I want to find all nodes in the graph that are adjacent to me. That is, they are neighbors of me. And keep this template in mind as we actually work on the solution here. Okay. So we're going to call this find adjacent. And node is the name of the node that we are trying to find. So we're going to have to first find the node, but also find all of those nodes that have this node as an out neighbor. So if our graph is empty, the answer is obvious. If the graph is empty, there's nothing to search for. So we should produce empty. Now, why are we producing empty? We are producing empty for the sole reason that we want to produce a list of neighbors. So in our base case, if the graph is empty, we produce empty. Now we have a few cases to consider. What if the current, i.e. the first node in the graph is equal to the node we are searching for? If that's the case, then I want to take all of the node I'm looking at, I want to take all of my out neighbors and add it to the list of all of the in neighbors that I find. So what I'm going to do is I am going to append, first we need to identify that this, of course, is the node that we are looking for. So we're going to use symbol equal to compare node to the name of this current node. Now, if I were you, I would actually create some helper functions to actually encapsulate getting the name of this node and the values of this node. Because if you don't, you're going to end up with all this first, second, first, and it's just really, really ugly. I haven't done that though, but you're welcome to. All right. Now, in the case where this is the thing we are searching for, we are going to append all of our out neighbors to the result we get from searching for this node as an out neighbor of all the other nodes. So I'm going to append all of my out neighbors to continuing my search for adjacent nodes in the rest of the graph. If you hear a lot of fans whirring, because I have a little old Surface 3 that is streaming its desktop to my Mac, it's kind of overheating, so you're just hearing my Surface's fan. And my dishwasher. All right, so we've handled the case where the current node is the one we are searching for. Now we need to handle the case where the node is not the one we are searching for, but we want to check your out neighbors to see, is one of your out neighbors me? Because if it is, that would imply that you are adjacent to me. So what we're going to do then is, if we are a member of your out neighbors, we are going to cons you onto the list we get from searching for more neighbors in the rest of the graph. Again, I apologize for the very poor network connection. If you're watching on Twitch in the live stream and experiencing a lot of difficulties, please do remember that I will be uploading the video to YouTube afterwards as well. And since that doesn't use a networked stream, it will be a lot better quality. All right, so we've handled 3 of our cases now. We've handled the case where we have an empty graph. We've handled the case where the node that we're looking for neighbors for is the current node. And we've handled the case where the current node is not the node we're looking for, but we are one of its out neighbors. We have one more case to handle, and that is, this is not the node we are looking for. And this node also doesn't contain us as an out neighbor. So in our else case, we are simply going to call find adjacent on the rest of the graph. There we go. Now let's run this. And I have the graph from the course notes already added here. So let's actually do some tests. So first off, I know that node A only has 3 neighbors, C, D, and E. There are no other nodes in the graph that have A as an out neighbor. Okay. So if I call find adjacent with A on our graph, I should only get C, D, and E, and indeed I do. Now I'm going to try find adjacent on node D. And what I'm expecting for this is A, F, and J. Now, why do I get A? I get A because I'm looking for not just the out neighbors of D, I'm also looking for the in neighbors of D. And D is listed as an out neighbor of A, which means A is an in neighbor of D. So when we call find adjacent, we indeed get A, F, and J. So there you go, an example of another function that is going to traverse a graph, which means we are going to visit all of the nodes in the graph. All right, one of the things that I want to make note of with this particular example here is that you'll note we only needed one function to do this. Some functions that deal with graphs don't need mutual recursion, don't need a helper function, and this is one such example. That's not to say that every function you could do with a graph will follow that. And in fact, the functions we're going to look at very shortly specifically don't follow that. So just keep that in the back of your mind. All right. So let's go back to our slides. And what we were looking at with our slides, we didn't leave off with a template. We were actually interested in discussing finding a path through a graph, because that's actually one of the most important things that you can do with a graph, is find a path from one node to another node, or determine that that path does not exist. Now, why do you want to do this? Well, if you consider that a graph could be representing something like a city map, I might want to know, if I was Google and you type in the source as being your address and the destination as being your friend's house, we need some way of determining, is there a path that goes from your house to their house? We can use a graph to do that. Similarly, we use pathfinding algorithms for things like networking. Network is actually represented by a great big graph. And when I send a message, or even when I'm uploading this video to Twitch, that data has to follow some path from my home network to Amazon. What path does it follow? Well, it is a graph algorithm. It's actually a rather complicated graph algorithm, which is covered in a 4th year course. It's pretty cool. All right, so we want to find a path. Now, I'm going to switch over here back to my tablet. There we go. And I'm going to move myself up here. And what we're going to do is we're going to erase some of these details. And it's going to take a minute to update for you guys. All right, so let's suppose I want to find a path from A to F. Is there a path from A to F? Well, how might I find a path from A to F? Well, we're going to start at A. And because that's our source, and I'm going to say, is my current node the thing I'm looking for? Well, A is not F. We're at the origin. We haven't moved anywhere. So I know that this is not the destination. So I need to know, okay, where do I go from here? Now, one option we can do is we can look at our neighbors, our out neighbors. Because while we are not F, maybe one of my out neighbors is F, or maybe one of my out neighbors has a path to F. So after I search myself and I see that I have no path, I'm not F, so I have no direct path to F. I'm now going to look at my out neighbors, and I'm going to start by looking at, let's do B, because it comes first alphabetically. So I visit node B, and I say, node B, are you F? Obviously, B and F are two different things, so this isn't going to work. Okay. Well, B isn't F, but maybe one of B's neighbors is F. So maybe there is a path from B to F instead of A to F. Because there's a path from A to B, so if there's a path from B to F, then there is by definition a path from A to F. So now I'm going to look at the out neighbors of B. You'll notice I'm choosing different colors to do this. There's a reason for that. So I'm going to again choose the out neighbor in alphabetical order, and I'm going to go to node D. And at node D, I'm like, is D F? Obviously, D is not F. Okay. So there's no, F is not an out neighbor of A, and F is not an out neighbor of B. But maybe there's a path from D to F. Because if there's a path from D to F, there's a path from B to F, and therefore there's a path from A to F. So I'm going to visit node D, and I'm going to say, D, what are your neighbors?
And so finally, I gotta choose a color here. Let's go with green. I visit the out neighbors of D, and D only has one out neighbor, which happens to be F. And I'm like, oh, this out neighbor is the thing I am searching for. Therefore, there is a path from D to F. And since there's a path from D to F, there's also a path from B to F. And therefore, there's also a path from A to F. Now, this particular method I've just showed you for finding a path between two nodes actually has a name, which I don't believe is mentioned in your course notes, which I think is woefully shameful. But its name is called depth first search. And it is not the only method that you can use to find a path from one node to another node in a graph. There is another one. It's called breadth first search. So this one is called depth first search because we're going to go deep into the graph to find it. And then if we can't find it, we're going to backtrack back up and find another deep path. Breadth first search is going to explore the neighbors of the origin before it explores the neighbors of each of your neighbors. So it's going to check B and C before it goes to D and E. So if we were doing breadth first search, I'm going to draw some rings here. And I think I've got this nice space thing. So this would be our first check with BFS. And then our second with BFS would be this one. And then in our third, we would check this. And finally, we would get F in the fourth. So these funny rainbowish lines that I've drawn on here are actually for breadth first search, not depth first search. But breadth first search, I'm not saying it can't be done with Racket. It's a little bit trickier to do. So we're going to cover depth first search instead. So let's go back here. Now, one of the things that you note is that at each stage of our search in the previous thing, we had to look at the neighbors of the current thing. So it would be very useful if we had a function that could be used to extract the neighbors of a particular node. So we have this lovely function here where we search a graph, and if the first key value pair in our adjacency list is the node we are searching for, then we're going to produce the second, that is the value of that element. Otherwise, we're going to recurse. Now, my only complaint about this particular function is this follows the simple recursive template, and you could have actually implemented this much more simply by using an abstract list function. Now, of course, it's not as readable once you use abstract list functions to the average person, but the simplified version of this is actually this one-liner down below, which is I chose to implement it as filtering the graph to find the node that has the name we're looking for, and then when I get the list that contains that, I call the second of the first. Now, of course, this is assuming that the node we are searching for actually exists in the graph. We're going to make that assumption. All right. So we've got our neighbors function. Now we actually have to think about how do I find the path given that. So what do we know? Well, we're going to try to find a path for this example from A to H. And as I said before, if A's neighbors are not H, there may not be a direct path going from A to H, but there may be a path going from one of A's neighbors to H. So we're going to check A's neighbors, and if A's neighbors are not H, then we're going to check each of those neighbors and say, do you have a path to H? And then we check their neighbors and say, do you have a path to H? Until we find one that has H listed as its out neighbor. And if we can follow that process, then we know we have a path to H that goes from A. Now, this kind of algorithm, depth first search, is a backtracking algorithm because what it's going to do is whenever you are unable to find the path, let's say you end up at a dead end, and your previous node that resulted in you getting into a dead end had more than one child, then what you're going to do is you're going to go back to the node that you originated from, and you're going to check their other children. Because just because you don't have a path to the desired destination node doesn't mean the other neighbors didn't. So we're going to backtrack and try again. And we will backtrack however many times we need to in order to keep finding the path. Now, if we actually visit every single node and we always fail, that would mean there is no path. The other thing I want to say is there is the possibility that there are multiple paths and all kinds of other wonky business that we'll keep track of a bit later. Okay, so I'm going to skip this slide here because it's not very useful. And we're going to start talking about how do we actually implement this find path function. So first off, we're going to call our main function find path. And it's going to be responsible for actually visiting a node and checking, is this the destination or not? Then, in order to choose which of our neighbors we want to visit next, we're going to use a helper function called find path list. And what you're actually going to find here is that we're going to be using mutual recursion. And this looks a lot like our finding a path in our evolution tree. Because remember, evolution tree, being a tree, is a graph. So there is going to be a lot of similarities between some of your tree algorithms and this find path algorithm. So without further ado, here is the implementation of find path. So this is the actual visiting of the node. It is here that we are actually going to check to see, is the current node we are at the node we are trying to go to? So if the current node's symbol is equal to the destination, then we produce the path that contains this destination. Now a path, remember, is going to be a list of nodes. So I'm going to produce a list that contains the symbol that is the name for the destination. If, however, this is not the case, then we need to check the neighbors of the current node. So in the else clause, you will see that we have a local, and it makes it kind of hairy. It's going to get worse. And we have made a constant where we are calling neighbors to get the neighbors of the current node. And then we have this very funny named question mark path that is going to search for a path through each of the neighbors of the current node and the destination. And we're going to call that find path list. We pass it the neighbors, the destination, and the graph G. Okay. After we have done that, we need to look at the result that that path variable has to determine, was there a path to our destination through the current node or through each of any of our neighbors? If path is equal to false, then there was no path through our neighbors, which means there is no path through us. So we're going to have the function produce false. If, however, there is a path, then we are going to cons our own name onto the result of that path and produce that value. That's the answer. So what then does this find path list, where we're looking for a path through our neighbors to the destination, look like? And here it is. It's on slide 19. What we're going to do is, if the list of neighbors is empty, well, then there couldn't possibly be a path because you were not the destination. Hence why we are looking through the neighbors of yourself. So if you have no neighbors, then we have either exhausted searching through all of the neighbors of the origin, or you simply had no neighbors and there's therefore, this is a dead end. So if the neighbors list is empty, we produce false, B, there is no path. Otherwise, again, you'll notice here the nested local, we're going to search for a path from this current neighbor. We're going to visit one of our neighbors and check for a path through it. And we're going to assign that again to this question mark path, which means if there is no path, it will contain false. And if there is a path, it will contain a list of symbols. So then we have to check and see, was there a path through this particular neighbor? If there is no path, that is, path is false, then we need to search for a path through one of the other neighbors. This is backtracking. We search for a path through this neighbor, and if there's no path through this neighbor, then I search through a path through the next neighbor. So I went down there, and then I came back up, and now I'm going to go back down this rabbit hole. If, however, their path was not false, then it is by definition going to be a list, and therefore there is a path through this particular neighbor. We produce that path. And that's it. That's finding a path. So let's actually trace through, not in a traditional way, but actually tracing through on the graph itself, trying to find a path between A and B. So we start with finding a path between A and B. And A is not the destination, so we're going to look for a path through the neighbors. So I call find path list on C, D, and E. Well, since there are neighbors in the list, we're going to choose the first item of that list and visit that node and check, is there a path from C to B? And, well, C was not B, so we're going to look at C's neighbors. And C's neighbors are empty. And so this was a dead end, and we're going to backtrack back up here, and now we're going to visit past possibilities through node D. So we visit node D, and now we're going to check to see if any of D's neighbors have a path to B, because D is not B. So I call find path on D's neighbors, which are F and J. And I'm going to choose to visit F first. So I visit F. F is not B. So I'm going to check, does any of F's neighbors contain B? So I call find path list on its neighbors, which is K and H. Then I'm going to choose K to visit, and I visit K. K is not B. And so what I'm going to do from here is I'm going to call find path on, of course, our neighbors, but we have no neighbors. And so this is a dead end. This produces false. We backtrack back to here, and now I'm going to visit H. When I visit H, H was not B, so I'm going to check the neighbors of H and see if any of my neighbors for H have a path to B. But H has no neighbors, so it's a dead end, and I backtrack back to here. Now, when I get to here, I have no more neighbors, so this is going to produce false, and this is going to produce false, and I end up backtracking all the way up to this line here. So I've completely exhausted searching all the paths through F, which is D's out neighbor. And now I need to check through D's other out neighbor, J. So I go through J. J was not B, I visited. And so I check J's neighbors. Well, J's neighbor was H. So I visit H, and H was a dead end, and I end up backtracking here. J has no more neighbors, so I backtrack again up to here. I have now checked every single one of D's out neighbors, which means I'm going to backtrack one more step back to this. And I'm going to check the next out neighbor of A, which is E. So I visit E. E is not B. So I check E's neighbors, which is K. I visit K. K is not B. So I visit K's neighbors. Oh, it doesn't have any. So that produces false. We backtrack all the way back up to here, realizing that we have exhausted all possible paths in the graph because there are no more neighbors to our origin. And so therefore there is no path from A to B in this graph. Now, why is this algorithm called depth first search? Because we go deep until we reach a dead end before we go wide to search the other neighbors. Okay, this works. Now, I want to talk briefly about some other uses of the code that you've just seen. This is totally irrelevant to you because you don't have an assignment 10 and because we lost a week of content due to this virus. Normally, we would have a final assignment that had you solving some kind of game. And you might be wondering, why are we suddenly taking a moment to discuss games when we're talking about graphs and finding a path in a graph? And that is because the states of a game are a graph. If this here is the state of the tic-tac-toe board and it's O's turn, there are 4 possible next states. You have 4 possible neighbors. I could put it here in the upper corner. I could put it in the middle. I could put it in the middle on the right, or I could put it in the bottom in the middle. There are 4 possible out neighbors from here. And I need to know which one of those paths is going to lead me to winning the game. And the same is true for chesses, the same is true for 4 kings, the same is true for checkers. You can actually represent these games as graphs, and then knowing whether there is a possible path for you to win is trying to find, can I get from my starting state to a winning state if I make this decision here? But of course, here's the particular problem. If we were to store every possible combination, that is every possible state of the game, there would be way more nodes in this graph than we could possibly store. Now for something like tic-tac-toe, it's actually not that bad. Okay, it's bad, but things like chess and checkers are significantly worse. So we don't actually want to solve this by storing an explicit graph where every single node is actually stored in some kind of adjacency list. Instead, what we tend to do is create what's known as an implicit graph. And instead of having a function neighbors that just grabs the value from the key value pairs, what we're going to do is we have a function that produces all of the neighbors on the fly. That is, it computes. Given your current state and some set of rules, it's going to compute a neighbor or the list of neighbors on the fly. So we're not permanently storing all of the possible neighbors. And then we can use a depth first search or a breadth first search from here to actually figure out, if I make this move, is there any situation where I could possibly win? Kind of fun stuff. Unfortunately, you're not going to get an opportunity to play with it. Maybe in the future. Or maybe if you're bored because you have nothing else to do this summer. All right. So that's enough of that little aside. Let's move back into talking about the graphs themselves. So here's the interesting thing. The algorithm that we actually gave you and the graph that we gave you for finding a path only dealt with graphs that have no cycles. So in particular, the graph we gave you had no cycles, and so find path actually worked. However, I can tell you that if there's a cycle, you're gonna have a really bad time. The algorithm we have given you, if there is a cycle, is going to go around and around and around, and it will never terminate. That's really bad. Now, it doesn't mean it always never terminates. No, it's just to say if there is a cycle that is ill-placed in the graph, that method we just gave you will never terminate. Let me show you how. So this is the graph. We have A, B, C, and D. So we have a graph on 4 nodes, and you can see it is a disconnected graph. D is not connected in any way, shape, or form to the other nodes. And the graph A, B, C is actually a cycle. A goes to B, B goes to C, and C goes to A. I want to find a path from A to D. Now you know that there is no path from A to D just by looking at this, but let's apply the find path algorithm that we already have. All right. So we start at A. A is not D, so I'm going to check if any of my neighbors have a path to D. Well, my neighbor list contains B, so I visit B. B is not D, so I'm going to check if any of B's neighbors have paths to D. So we call find path list on the neighbors, which are C. Then we visit node C, and we say, okay, well, C is not D, so let's see if any of C's neighbors have a path to D. And here you see the problem. We end up with C's neighbors being A, and then we visit A, and we're back to the origin again, and this will actually never terminate, ever. So that didn't work. So how are we going to fix this? Well, actually, it's quite easy to fix. You simply have to keep track of which nodes you've already visited. Because the reason, if you go back to this, we don't keep track of what nodes we've already visited. And as a result, we end up visiting node A again. If we kept track of which nodes we had visited, and before we visit a node, we check, hey, have you been visited before? And if you have been visited before, maybe we shouldn't go through you because we already know there's no path. And so what we're going to do is we're going to add an accumulator that's going to keep track of all of the nodes that we've already visited. And that will get rid of our cycles. So it's a teeny tiny modification. Let's look at find path list. So first we're going to add an accumulator called visited. And that is a list of nodes that we have visited on our current search. And before we check for a path through one of our neighbors, one of the neighbors in the list, we're first going to check if the neighbor we're going to be searching through is in the visited list. And if the neighbor we're searching through is in the visited list, that means we've already been there, we already know the answer is no, and so, or there is a cycle. So what we're going to do then is we're actually going to skip searching this neighbor and look at any of the other neighbors. And then the rest stays the same. Now what's interesting is this is using a cumulative recursion because we've got this accumulator, but you will note that in this function we never actually modify the accumulator. That's because find path list doesn't actually visit the nodes. It's the other function that visits the nodes. This is just responsible for choosing which of the neighbors we're going to visit next. So what we need to do then is update find path. We're going to split it into two functions. And yes, they're all top level. And yes, you can make them local if you so wanted to. So we have our find path accumulator. And here you see we've got our visited list. And this is the function that actually visits the nodes, which means that this is where I want to update the accumulator. So when I call find path, and I pass to it my list of neighbors, I'm going to cons myself onto the list of visited nodes. Because I am visiting this node called origin right now. Therefore, I have visited it and I need to update the visited list. And then our wrapper function simply passes empty in as the initial visited list because we haven't visited anything yet. And there we go. But does it work? So going back to this graph again, we keep revisiting this silly graph, and we want to find a path from A to B. And I'm not going to go through this in any kind of great detail because we've already gone through this particular graph a fair bit. This is actually the exact same trace that we had before. The only thing you will note here is that the accumulator now contains the list of the nodes that we have already visited. And what's interesting about the accumulator is it's the reverse of the path we took to get to the current node. So if I am visiting node C, well, I got to node C by node A. And if I am visiting node F, I got to node F as A, D, F. And if I got to node K, then I got to node K by visiting A, D, F. So the accumulator is actually the reverse of the path you took to get to that node. So that's kind of cool, actually. Can be useful too. So the only thing this is actually proving, however, is that by adding this visited accumulator, we haven't broken anything because the path actually didn't change. So what we actually want to show you is that we haven't broken anything in terms of the cycles. So have we actually stopped us from following a cycle round and around and around in circles? So let's go back to our graph where we're trying to find a path between A and D. And we have a cycle between A, B, and C, and D is not connected. So we start with A, and of course this was not our destination, so we're going to look at A's neighbors, and we set the accumulator to be A as in the node we have visited. Now, we are going to look at the neighbors and we see B. Well, B is not a visit. We haven't visited B yet. So let's visit B. So we visit B and B is not our destination. So we're going to check for paths from C to D and we update our visited list to indicate we have visited both A and B. Now, while we are visiting C, we realize C is not D. And so we are going to check for paths between our neighbors and D. And inside find path list, we see our neighbor A is actually in the visited list. And so what we are going to do is stop and we produce false and we don't end up following the cycle. So by making that teeny tiny change of keeping track of the accumulator as being the list of visited nodes, we don't end up following cycles. And we're happy with that. That's really great. I'm actually not that happy with this. I'm going to go back. Look at this particular piece of code, this particular trace. What you can see here is that when we did this original trace, and this is for both of the two implementations of find path that we have, when we get to node K, we know the first time, we know there's no path from K to B. When we get to node H the first time, we note the fact that there's no path from H to B. So why then do we try to find paths through H and K again? There's no point in doing that. We already know that there is no such path. The problem that we have with this particular algorithms that we've shown you so far is that it will possibly follow an exponential number of paths before determining that there is no such path. Now, does that mean that those exponential paths were all completely unique? No, it's entirely possible that we actually keep revisiting the same nodes over and over again that we already knew the answer to. So we have this beautiful example actually in the slides. And what this example is doing is it's showing you how we arrive at the possibility of having an exponential number of paths. So here we have a graph that is made of a number of diamonds. What do we mean by diamonds? Well, you have the pinch points, and then there are two out neighbors from each of those pinches, and then from those neighbors, they go back into a pinch point. Now, if we were trying to find a path from A to Z, there are many paths that we would take. We can first, let's go A, B, C, D1, E, E1, and so on and so forth. And when that fails, we'll backtrack to E, and then we'll go from Y, we'll go back to X1. And from X1, we'll go back to X. And then we realized, oh, there's another way we can explore from X. We could go to X2. And then we go to Y. Wait, we already know there's no answer at Y. And then when that doesn't work, we go back and we go back to W. And from W, we go through W2. And then we'll go through X1 and X2 again, even though we already knew there was no path. So what I'm trying to say here is we have D diamonds. And at each of these diamonds, I'm going to use the diamond to be the beginning pinch point. Each of those diamonds, there are two choices that you can take. You can go up or you can go down for each path. I'm going to tell you that gives you 2 to the power of D possible paths from the origin to the end to explore. Now, why is it 2 to the D? Many of you may be familiar with the concept of binary numbers. Well, actually, this graph of diamonds is actually a binary number. Each of these points here, each diamond is actually a digit. And with each digit, there are 2 possibilities. We can go up or we can go down. The digit can be 0 or the digit can be 1. So, for each diamond, there are 2 choices, 0 and 1. D diamonds, 2 to the power of D possibilities. So for this graph, in order to determine that there is no path from A to Z, we will actually explore all 2 to the power of D paths. Now, maybe that doesn't seem like a big deal to you. Really? So let me tell you something. If there are only 12 diamonds, there are 4,096 paths for 12 diamonds. 4,096 paths. That's a lot. If there were more diamonds, if there are 32 diamonds, you are looking at over 2 billion possible paths. This is not a very efficient method that we've shown you for finding a path from an origin to a destination. Can we do better? Obviously. As a side note, you'll notice that I took a graph and I transformed it into another kind of problem that we know the answer for. This is actually something very common we do in computer science, although you probably won't see this again until CS341. Where we are actually translating one problem to determine a solution to one problem, we translate it into another problem where we do know the solution. That comes much later in CS. All right, so what I need to do then is, it would be really helpful if I kept track of the paths that I had been on, and then instead of revisiting a path that I have already been on, I'm going to check to see if I've already been on a path through that node. And if I've already been on a path through that node, that means I've already exhausted all of the options through that node. And I know that it's not possible for me to find the answer through that node. So what we're going to do is we are going to keep track of the paths that we fail on. So what are we going to do? Well, first off, our previous solution actually does two things. If there's no path, it produces false, so we wouldn't actually know what paths we fail on. We now want to keep track of the paths that we fail on. And that means that we need to differentiate between a path we succeed on and a path that we fail on. So we've decided to solve this problem by actually introducing two structures. We have the success structure, which is a path that actually leads us to the answer, and a failure structure, which is a path that doesn't work. Why do we use these two structure representations? Now we can actually use them to keep track of a fail path and a success path. And then by having them structures, we get the predicate for success and a predicate for failure, which we can use to determine is the result a success or a failure, so that we can still present to our user the same behavior that we had from the other functions. All right, so let's go back into find path list. And now we're actually going to make a few tiny changes to this. So if the list of numbers is empty, we know there is no path through this particular node. And we know then that the path contained in visited is a failing path. And therefore, we are going to make a failure structure that contains the path visited, because this path did not work. All right. And what that means is that through the origin of this particular list of neighbors, there is no path to the destination. So then if, however, neighbors is not empty, we're going to check the visited list to see, does it actually contain the thing we are looking for? That is, does it contain the node we want to visit next? Because if it does, it means there's a cycle we've already visited. We don't want to go down that route again. So what we're going to do is, if this current neighbor is a member of the visited list, then what we are simply going to do is we are going to go to the next neighbor. Now, otherwise, if we haven't visited this neighbor before and the neighbor list is not empty, then we're going to search through a path through the current neighbor to the destination, and we store that in this result. Now, result is going to be one of two things. It's not going to be a list or false. Now it's either going to be a failure structure or a success structure. If it is a failure structure, then I am going to need to look through the remaining neighbors, and I'm going to pass the visited, the accumulator is changing in this case. Now we are actually setting the visited list to be the path that we failed on. And so that's going to include all of the nodes that we visited so far, and it's going to include any of the nodes we visited beyond that we know we couldn't get to the destination to. So it's actually cycle prevention plus plus, so it's really, really great. If, however, the result was a success, then we know for certain we have the path and we're just going to produce the result. Very teeny changes to find path list. Now let's go and update the accumulator. All right. So through the accumulator, we're going to have to make some pretty big changes as well. So first off, we are going to, if the origin is equal to the destination, we have succeeded in actually finding the path. And so we are going to take the destination and make a success structure that contains that path there. If this is not the destination, then we need to determine if we can find a path to the destination through any of our neighbors. So just as before, we compute our neighbors, and then we are going to search for a path through each of our neighbors and store that in result. Now, look here, we're updating the accumulator the exact same way that we did before, marking the fact that we have visited this origin node and appending that onto the accumulative visited list. Now, when that actually produces a value, and we are then going to need to check to see is result a success or a failure. If it is a failure, we're going to produce the result. And if it is a success, we are going to produce a new success structure where we cons our origin, i.e. this node, onto the path that we get. Because result contains the path from our neighbors to the destination. That doesn't include us, and so we need to include us in that path, and that's what you're seeing done right here. And there you go. We have updated the cumulative find path function to actually keep track of failure paths and success paths. We need to make one more change. And that last change is in our wrapper, because we don't want to expose our user to the fact that there is this concept of a successful path and a failure path. We want that wrapper function to still produce false if we fail to find a path and produce just a list of nodes if we do find a path. So what we're going to do is we're going to compute the results using this local of actually searching for a path. And then we are going to ask, what type of structure is it? If it's a success structure, then we are going to return just the path field. And if it's a failure structure, we produce false. And so this wrapper is actually going to take that internal data form we have used and turn it back into what the user is actually expecting. And this is actually something you can totally do anytime you need to. Maybe you need to add some extra data types to make the computation a little bit easier, but you want to hide that from your user. You can totally do this, and it works just fine. Okay, so we're not going to trace through that example there. I would actually, and I know we still have a lot of time left here, but my tablet here is a little bit slow to draw on. So what I want to do then is to just mention to you that we've shown you 3 different implementations of find path. The first one couldn't handle cycles. The second one can handle cycles, but like the first one, it also had us potentially exploring an exponential number of paths. If you actually trace through the third one that we just went through, you will find that it not only stops cycles, but we're going to visit significantly fewer paths. Now you may be wondering, is that as good as you can do? And the answer is, for finding a path, absolutely not. There are algorithms that can be even more efficient than what we've shown you at finding a path from A to B. There are some really cool randomized search algorithms. There's one of my favorites is A-star search, which is for a graph, and I like breadth first search. These are all really, really cool things. And if this kind of algorithm interests you, CS341 is going to be a lot of fun for you, because you are going to do a ton of graph algorithms. It's really the graph course, I suppose you could say. And you'll also, by the way, do some graph stuff in Math 239, which is combinatorics and some graph theory. And there's all kinds of really cool graph theories that are super helpful for computer science in there as well. One of my favorite theories in that particular course is coloring, graph coloring. That's a really fun topic. All right, now I just want to talk to you a little bit about different uses for graph algorithms, not just find pass. I've already told you a few uses for find pass, but I want to tell you about some other things that you can actually do with graphs, which are kind of cool. So we've shown you that you can use a graph to represent states in things like board games and determining which move gives me the highest probability of actually being able to win the game. So you can absolutely use a graph to represent a game. But a place where I use graphs is actually in flood fill. And that may come as a bit of a surprise to you. So I'm actually going to draw this out here. But first I've got to actually erase actually I guess I don't have to erase, it's OneNote. Let's go back over here to my tablet. It's going to take a minute to update, I apologize. It's a little bit slow going from my old Surface over Wi-Fi. Oh, it's being very, very slow. There we go. We've got our grid here. So I'm going to show you that flood fill also uses depth first or breadth first search to work. This is actually pretty cool. So I'm going to start coloring some of these pixels in. Okay, and in a minute here it'll actually show up and you can actually see what we are trying to flood fill. For the record, they told me I needed to have a gigabit Ethernet in order to make this work. Of course, I don't listen very well. So you can see here we have a picture. And each of these little squares are actually pixels. And let's suppose I want to flood fill the white area. So maybe starting in the upper right corner, I want to flood fill. Okay, how do you actually do the flood fill? Well, first off, let's use a graph algorithm to do flood fill. And by the way, this is actually how I implement flood fill. So what I do is I consider each of the individual squares in my image, each of the pixels, I consider to be a node in the graph. And then each of my pixel nodes have a set of neighbors. Now, in our flood fill, we usually only consider our neighbors to be the left pixel, that is the pixel immediate to our left, the pixel immediately to our right, the pixel immediately above us, and the pixel immediately below us. So, my neighbors are, let's say this is our starting point. I have an up neighbor, I have a down neighbor, I have a right neighbor, and I have a left neighbor. So those are all my neighbors. Okay. So I first check. The starting point is the place I want to start coloring. And I check, are you the color that I want to color? Oh, you're not. Okay, well, I better color you. So I color in this. And now I actually have a tendency to use breadth first search to do this, but you can use depth first as well. It's a little harder to use depth. Excuse me. Now I have to look at my neighbors and I have to ask my neighbors, hey neighbors, are you white? And if you are white, have I colored? That means I haven't colored you yet. So let's start by arbitrarily going to the up neighbor. So I go to my up neighbor. Actually, let's use depth first search here. And I color my up neighbor. And now from my up neighbor, now that it's colored, I need to look at the neighbors of my up neighbor. It has two, a left and a right. Now it has a down neighbor as well, but we are going to mark the fact that we already covered that down. And I look to my left and I see that the left is orange. That is not the color I'm supposed to be filling in. So now I'm going to look to my right neighbor. Oh, you're white. We better color you. And then we color in the right neighbor. And now from the right neighbor, I look at its unvisited neighbors. And I see that there is a down neighbor. And so I look at that neighbor. And I see that it's white. And so I am now going to color it in. And now that I've looked at its neighbor, or that particular node has been colored, I look at its neighbors and I see that it either doesn't have a neighbor or all of its neighbors were colored already. And so I backtrack back to X, which is the last node that has unvisited neighbors. And now I go down and I say, oh, you're white. That means I should color you. So then I go down and I color this one in. And then I'm going to look at its neighbors, and I see all of its neighbors are orange. And so I backtrack up to the left neighbor here. And then I color this one. And then we repeat the process. This is a graph algorithm. Flood fills graphs. Because what we're doing is we're considering each and every single pixel in our image to be a node, and then our neighbors are up, down, left, and right. And so we can apply things like breadth first and depth first search in an image to do algorithms like flood fill. Or flood fill is actually really closely related to selection. So if you wanted to select a region, a lot of the time we're actually using a flood fill like method. So these algorithms of searching for paths, doing things like depth first search like we've done in these slides, they are everywhere in your life, and they are pretty cool and pretty interesting to know. And hopefully you continue on in CS and take CS341 and Math 239, and you learn all sorts of more interesting stuff about graphs. All right. So with this, that is the end of the graphs module, and sadly this is also the end of the CS135 offering for winter 2020. I know normally we would have had 2 additional lectures, but due to the university terminating all in-person lectures, they've actually required us to remove an entire week of content from the course. Hence, if this seems a little hurried, that's actually what's going on here. If you do, you'll notice that we didn't cover that history module, and if history of computing is something that interests you, I would highly recommend that you go out and read that module on your own. And if you have any questions or want to know more, don't be afraid to reach out to me. Computing history is something I actually find really interesting, and I have spent many a day at the Computing History Museum down in Mountain View, which is a really great place. So that being said, I hope that you have found this course at least to be interesting. I hope that you have found it useful. I hope that you are walking away with some better experience with debugging and how to approach the solving of problems. Now, I know that you may not go out in the world and use Racket. It's not exactly a language that industry uses. But the ideas that we have conveyed here, they go beyond a particular language. You can take recursion and you can use all of these recursive algorithms that you've used in C, in C++, in Python. Recursion is not so common in industry. A lot of the time they use loops instead, but the ideas are still there. And the concepts of how do I solve a problem, that's a universal language. So I hope that you have actually found this useful and interesting, and I do hope that you either continue with your computing studies, or I hope at the very least that you start doing some side projects in computing to see what kinds of cool shit can you actually do. And with that, then I wish you the best of luck in your future terms, your future careers. I hope that you are all staying safe and healthy and not going stir crazy. And please, by all means, don't be afraid to reach out if you have questions or you're curious about certain aspects of industry. By all means, you have my email address. Just send me a line. I'm happy to answer. All right. That then is the end of CS135.